So, and of course, it's being recorded. I am delighted to introduce our first speaker, Jens Jackwerth. He is a professor of economics at the University of Constance, Germany. He has held positions at London School of Economics, the University of Wisconsin, the University of Zurich. Professor Jackwerth's research, of course, is in the area of asset pricing and derivatives. Especially, he has made outstanding contributions to the literature on recovering investors' risk aversion from option prices, mispricing of derivatives, and market manipulation. Professor Jackwerth is the recipient of several awards and distinctions, including Inquiry from UK and Institute of Quantitative Research in Finance. Professor Jackwerth is going to talk about Ross's recovery theorem and whether it works empirically. His paper will be discussed by my colleague Sanjay Navolkar later. Jack, it's all yours. Jen.
I'm trying to share my screen.
Yeah, and you should be able to share your screen.
Okay.
There you go.
Okay, I'm on?
Yes,
beautiful.
Thank you.
Thank you very much for having me here and for participating in this very nice conference. I'm very glad to talk a little bit about Ross recovery and if the Ross recovery theorem actually does work empirically. Now, this is joint work with my old PhD student Marco Menner, who is now at ESADE in Barcelona, and let's see what's happening. Now, the motivation here is that the Holy Grail is really to forecast future returns of a stock or an index. And if we look at the main pricing equation, then we are having this triangular relationship between state prices, pi, the pricing kernel m, and the physical probabilities, p over here. And it's quite obvious from the simple mathematics of what we are looking at here that state by state, one can normally infer one quantity from the other two, but you need to know two in order to get the third. And there has been some earlier work, Alvarez and German, and Lars Hansen has also worked on this, that one can maybe learn a little bit more about two of the quantities from only one remaining quantity. And namely, there has been work, and the idea is to decompose this set of state prices into the pricing kernel and at the same time the physical probabilities over here. And Ross 2015 in the JF article then actually suggests one particular implementation, and there was a little 12-state, essentially a worked example that did not turn out to be really working very well. And Ross acknowledged at the time in the JF article that, look, this is mainly a theoretical contribution. It's kind of a proof of concept, and then let's leave it to other people to actually sort out the nitty-gritty details. And I felt he was speaking directly to me in that this is what I'm good at, and he is smarter. Actually, years and years ago, he interviewed me at Yale, and it was an intriguing job interview because normally you present yourself as how good you are, and he presented himself and told me how good he is, and I'm like, well, this is kind of given, but okay, I'm moving away from the topic here, so let me rein back in and see where we are heading here. So what I tried to do together with Marco was then actually to implement Ross recovery in a more serious way, to really go to the data and try to work and wrangle the data in the best way possible to give the method not only this core structure that he implemented based on monthly data sets, but we wanted to go to a finer gradation of dates in order to get more equations and then get better results that way. Now, one thing we noticed right away was that Ross 2015, he needs very strict assumptions in order to make this pig fly, decomposing these state prices into two components instead of having two and going for the third. You need some kind of structure. And the paper was somewhat opaque on what exactly are these assumptions, and in particular, which of these assumptions really matters and which one does not matter. And this is what this paper is about. Some of the assumptions are very strict, and some of those assumptions do not hold very well. And this is what I want to talk about. So the basic summary of what I'm now going to do is I take Ross 2015 seriously. I take it to the data in a careful way, as careful as I can be, and I get physical probability distributions in a forward-looking way. And this comes out of the Ross 2015. And I then ask the question, well, if this is the physical probability going forward from now to, say, in 1 month, and I can also look at the future realized return, that is 1 month later, I can look at the return that actually happened during that time. Are those future realized returns compatible with the recovered physical distribution? And in general, they are not. Okay? You're predicting one thing, you're predicting a physical distribution, which actually turns out to look very, very similar to the risk-neutral distribution. And you can already guess if something looks like the risk-neutral distribution, then it is not the physical distribution, and the future realized returns do not stem from that forecast physical distribution. That's our short result. Now, what does Ross Recovery need, and where is all this going wrong? First, Ross Recovery needs what he calls transition state prices. And let's work here in a very simple example just to nail down the concept. We're in state 1, and state 1 is the true state we're in right now. Say the S&P 500 is at 1,000. And then in 1 month, it can go to 1,000 or 900. And this is the usual perspective of what we are always facing when we're recovering distributions from option prices. You're standing today in a state 1, and in the future you can have several states. Now, this is not good enough for Ross Recovery. What Ross also needs is the set of hypothetical probabilities if you were positioned in state 2 today. You're in state 1, you're not in state 2. But if you were in state 2, imagine the situation and then try to imagine which kind of probabilities emanate from this alternative state 2 and then go forward into the future. You need those probabilities as well. Right? And this is one of the big bugbears of what is happening here. We are having very, very little information on how to nail down all these hypothetical probabilities considering and concerning states we don't observe. So this is one big problem, and I will talk about that some more. So he makes the following assumptions. The transition state prices, pi ij, are time homogeneous. This he needs in order to get essentially enough equations going so that the whole estimation can work out. If you were to allow these pi ij's to also depend on time, you cannot solve the problem. So what he says is, well, every time period is essentially the same. The evolution over the first month is exactly the same as the evolution of probabilities over the second, over the third, and so on. And that allows us to aggregate the equations and then solve for the transition state prices. They also have to be positive. This is actually a fairly benign restriction that we can easily satisfy. And the third one is again an ugly restriction in that it's an assumption that actually matters and that really nails down how the pricing kernel looks like. So he needs to make an assumption, a very strict assumption on the SDF, on the stochastic discount factor, on the pricing kernel, and that it has to look in this particular way. So the pricing kernel is the ratio of quantities he will later identify and associate with marginal utilities. And it is always the marginal utility of where you end up divided by the marginal utility of where you are at right now. Okay? So you're going from state I to state J. And there is some kind of discount factor. Now, with all this in place, with all these assumptions in place, he then formulates an eigenvalue problem via the transition state prices pi ij. If you have the pi ij's, then you can set up this eigenvalue problem. It only has one unique solution for the case where this pricing kernel, mij, is strictly positive. You can have other solutions where the pricing kernel is negative, but he concentrates on the one reasonably enough where the pricing kernel is all positive. Then you have one unique solution. And this unique solution delivers the pricing kernel, mij, and also the physical probabilities, pij. And those are the ones I'm after because I want to then check if what these pij's say, what they say about how the future of the index is evolving, does that have anything to do with what I can see exposed, how the index actually evolved? And it does not work. That's the whole point. So the proof of the pudding is in the eating. What we do is we fit transition state prices to data on the S&P 500 options. So this is my beloved data set. What is really nice, I can even throw in the old Berkeley options database data from 86 to the 90s, to the mid 90s when option metrics is also starting in 96. But I also have the old data, so I can go for another decade. I do all the standard filters, so leave that to the paper. I don't want to dwell on that. And I use Ross Recovery to find the physical probabilities at 380 monthly days. And then I shift 1 month out and I look again at the monthly physical probabilities. And I statistically test if future realized returns do indeed come from those recovered physical transition probabilities. And I also want to answer a little bit the question, since it does not work, why doesn't it work? So let's see how we're pulling this off. We have implied volatilities. Here I'm showing you one pretty random day, February 17, 2010. Other days look similar. There are bid and ask volatilities, but of course, I don't have them at every point. So what we're doing is we're fitting a very smooth implied volatility surface on a very fine grid of moneyness levels and maturities. So there is some interpolation, extrapolation going on here because I don't want to be limited by the rather coarse nature of what I observe in terms of the option prices. Quite easily, I can go from implied volatilities to the spot state price surface. So from implied volatilities, I have this fine surface here. I can use those implied volatilities to make the transition to option prices. So then I have a super fine, very smooth option pricing surface. and I use Green-Litzenberger to take two derivatives with respect to strike, and I come up actually right away with a spot state prices pi that I can observe. I will not, during this talk, really distinguish between the state prices and the risk-neutral probabilities, given that this is a 30-day horizon and an interest rate which is virtually zero. One looks exactly like the other. So for all practical purposes, the state prices pi and the risk-neutral probabilities q are just one and the same. In the paper, I'm more careful and do it all right. So we see, of course, with very short maturities, you're having a rather peak distribution. This is a risk-neutral distribution now, and then it goes wider as you recede into the distant future. Yeah? Now, how do we get these transition densities? Right? We have the spot densities, and we have them at different points in time t, and I can grade that surface very finely. And what the transition state prices are supposed to be doing is, if you through multiply one spot density, say the one at 6 months, with the transition probabilities, you're moving out to the 7-month spot density. So spot densities I find in the data, and I'm asking myself the question, given all these finely graded spot densities and their partner 1 month later, let me find a transition matrix, pi ij, and here it's really important that we have this time homogeneity so that I can aggregate across all the different points in time throughout 1 year, which is all positive, that makes this actually happen. Right? Let me find something that supports this transition from one spot density to the next spot density, always 1 month apart, and then I shift by a few days, 2 or 3 days, actually here 2 business days I shift, and I do the next pairing. Right? So if I have the 6 months density and I connect it to the 7 month, and then I do the 6 month plus 2 business days, and I shift that to the 7 month plus 2 business days. And I find in between these transition state price matrices. This is how they look. Okay? It's a matrix. So it has the starting states. Those are the I states, and those are the J states over here, the state in t plus 1 month. So I'm going from here and I'm ending up here, and it's a bloody mess. Right? The transition state prices do not really look very pretty. They have some kind of structure which we would expect, namely, there is some kind of diagonal structure, which makes sense. If you're in a particular state today, say 1, then the chance that you're near 1 month later is actually higher than you being far away from 1. Okay? So we would expect that this that these matrices should have a strong diagonal structure, but they do not. Right? Look at this area out here. So if you have been doing horribly today, there is a very good chance that you end up in a very, very high state 1 month later. That is what the optimization says, even though it doesn't make terribly much sense. Why does the optimization end up with results like that? Because for option pricing, it completely doesn't matter. Right? Putting probability weights into weird regions like that, which do not matter for the pricing of the options, does not affect the fit of the options. It does not affect the spot densities one way or the other. And because of that, the optimization is basically free to allocate all these off-diagonal elements. And if it wants to have them high, let them be high. I will calm down the surface momentarily. Because again, the point was not to snipe at Ross. The point was give the method a fair chance and help the method as far as I can, and then see what's happening. Here, I'm interjecting briefly with how we then actually find out if the recovered physical distribution is consistent with the returns. If I have a physical distribution P from Ross Recovery, I plug in the future observed return and I get out a percentile. Okay? Given the forecast from Ross Recovery, I can work out the percentile of what actually happened. I look at all those percentiles, I shift 1 month out, repeat everything, I get another percentile. So I get a sequence of all these percentiles, and if the physical spot distributions P from Ross Recovery are actually any good, then these percentiles should be distributed uniformly. And this is what I'm testing. And I'm using a bunch of tests, Berkowitz, Knüppel, Kolmogorov, Smirnov. Results are largely the same. And this is what comes out here. The method I described, the one with the weird surface, is this one here, is Ross Basic. And the p-values are super, super low no matter which of the tests you're using. So if you're using the transition state prices I just showed you, you're getting the p probabilities for the prediction. It doesn't work. Reality is not compatible with Ross Basic. So let's do a little bit better. Ross Bounded is next up. There we say the row sums should add up to 0.9 to 1, which means the monthly interest rate should lie between 0% and 10%, yeah? Which on an annual basis is already really, really high. It still doesn't work. Ross unimodal then says it needs to be all positive, and the row sums are bound, so the interest rates cannot be too ridiculously high. They can still be ridiculously high, but not super, super high. And everything needs to be unimodal. So here in this diagram, I insist on unimodality. I insist that the highest probability is along this diagonal. It still doesn't work. And then there is a cute method I don't want to go into right now, Ross Stable, that is eliminating some of these far away estimates. And even that doesn't work. Now, what does work, and this is, of course, a little bit disconcerting, is a simple power utility specification, okay, which is straight from Econ 101 with a gamma of 3 for the exponent that I cannot reject. Or if I simply use the historical return distribution, I just say, well, I'm looking at the last 5 years of monthly returns. I smooth them a little bit with the kernel smoother, and then I stick everything back in, and I say the next month return is drawn from what happened during the last 5 years. That also I cannot reject. I interpret this a little bit along the lines of, if these really silly, simple methods cannot be rejected, then it's even worse that Ross Recovery can be so strongly rejected. So it doesn't work very well. Looking at the timeline, let me try to get to the end here. Results are robust, and I leave it to you to study the paper and trust me on, we kicked a lot of tires and the referees made us kick even more tires, and it survives. So why doesn't Ross Recovery work? What is going wrong here? The main culprit is that the recovered physical probabilities are too close to the risk-neutral probabilities. When I feed in the spot density into this whole system, inside the spot density, of course, I have the risk neutral probabilities. But Ross recovery, because it doesn't have any idea about where the physical probabilities should be located, does not see any need, optimization-wise, to move away from the implied probabilities, from the Q probabilities, from the risk-neutral probabilities. You feed it risk-neutral probabilities, you ask it to come up with a set of probabilities, but you do not tell it anything about what these other probabilities, the physical probabilities, are. You don't feed it historical returns, you don't feed it a risk premium, you don't tell it anything. Well, so it just essentially gets stuck at the risk neutral density and doesn't want to deviate from that. If the risk neutral probabilities and the physical probabilities are virtually one and the same, then the pricing kernel is awfully flat. Right? Essentially, you get flat pricing kernels with Ross recovery. Also, the pricing errors for the options are rather large. What does that mean? Well, that tells us that the transition probabilities are not time homogeneous. If they were, if you could use the same pi ij matrix for each and every month of the year, then you would actually be able to price all options throughout the year. But the long-dated options want to be priced differently compared to the short-dated options. Because of that, you need different transition probabilities at the short end and at the long end. If you check for these pricing errors, they tend to be fairly tight and small at the short end and then go much larger at the long end. This is what it looks like if you actually graph these claims. So for our sample day, February 17, 2010, I'm plotting the state prices. So the black dotted line is what comes from the options. And the transition state prices, that is what I fit. So it's fairly close. And the recovered probabilities, the red ones, those are the P probabilities. They should be located to the right. They should be right shifted because of the risk premium. And they should have actually not this leptokurtic left skewed shape, but they should be more normally looking, right? From anything we know about the physical distribution from our other work. And here they don't. If you divide them into each other, you're getting these strangely flat pricing kernels. And let me wrap up at this point. So in my view, Ross recovery is a fascinating concept as it allows to extract both the pricing kernel and the physical probabilities from state prices at the same time. However, empirically, it does not work as the future realized returns do not seem to be drawn from the recovered physical distribution. Right? So what Ross predicts, the P distribution under Ross, is simply too much like the Q distribution. Right? He says reality is more or less the same as the implied distribution, but reality is not. Reality is more normally distributed. Reality is right shifted because of the risk premium. And if you then feed those future realized returns into the predicted physical distribution P, and you're looking at the percentiles are then not uniformly distributed on the 0-1 interval, but they're severely different from uniformity. The severe assumptions and a lack of identification are the causes for these failures. So let me wrap up right here and see that we get some insights from the discussion, and then we can talk a little bit about the paper in the Q&A. I'm standing by. Now let me stop the share here, and I'm muting as well.
Well, thank you very much. And you are exactly on time. I appreciate that. So I'm going to pass it on to Sanjay, my colleague, who's going to discuss the paper, and then we'll have the Q&A. Sanjay? Sanjay, you're on mute. I can unmute you here.
I don't, yeah, now I'll share it again. So
Yeah.
there we go. Okay. So thank you. Thank you, Hussein and Jens. That was great. They did a great presentation that you made, and I'm going to make some very similar points. Let me begin. So the first thing that I found when I read your paper was that it was unusually clear, concise, rigorous, and meaningful. And I have to say that I don't always find every finance paper having all four qualities. So, you know, this was a great paper to read, and I would definitely recommend it to our PhD students if they even want to understand Ross recovery in like 3 equations, which you did, and it was very good to read. Then let me see. It confirms what your paper we already suspected with a number of theoretical and empirical critiques. Let me minimize this because I'm seeing your pictures. But unlike many other papers, this paper tests Ross recovery more directly. There are other papers that test things like if the permanent martingale component is volatile or stationary, but this paper directly tests the probabilities, which is very nice. And so it's one of my favorite empirical papers on Ross recovery. The authors provide an empirical critique of Ross. They test whether the physical probabilities recovered from today's S&P 500 option prices are compatible with future S&P 500 returns. And specifically, they are testing the null that future returns are drawn from the probability distributions recovered using these theorems. And there is the Ross original, then there are some extensions like the Jensen paper, which is the Ross table. The authors reject this hypothesis strongly using 4 different density tests: the Berkowitz test, the 2 versions of the uniformity test introduced by Nuppel, and the Kolmogorov-Smirnov test. Further, they show that means and variances of the recovered distributions cannot predict future returns and realized variances. So most empirical critiques of Ross theory began with the seminal work of Borovica, Hansen, Sheinkman. And that was like a little bit of a shocking result when they showed that the Ross assumptions imply a degenerate martingale component equal to 1 in the long-term factorization of the STF in Hansen and Sheinkman. Now, this is an interesting implication on the interpretation of the measure recovered by Ross. There is an interesting implication that this measure may not be the P measure, it may be the long run forward measure, which is what was found later. So the above result is inconsistent with the lower bound on the martingale components derived by Alvarez-German and Bakshi-Chabiyo. Obviously, these lower bounds are very volatile, so it cannot be a constant equal to 1. Now, with only 15 minutes, which I might have just 12 minutes remaining, let me just say what I will focus on. I'll be focusing on why Ross recovery fails. And you've already given 3 reasons: the shape of the SDFs, which are not U-shaped in most cases. Then in some of the cases you consider, which is Ross bounded and Ross unimodal, in which you put economic constraints. In these, there are huge option pricing errors. So the option prices in the parallel universes that are needed in Ross theory will not be consistent with those in the current universe. And then Ross basic is very sensitive to small perturbations in current option prices. Those are the 3 reasons given by you. I just want to take a more theoretical stance and really go dig deeper into what are some of the reasons for failure of the Ross recovery theorem. So my first point is that the theory itself is inconsistent. And I'll make a case that motivation of the theory contradicts the assumptions of the theory. So Ross gave assumptions under which the P measure converges to either Q, which we know under a flat term structure, and under a non-flat term structure, based upon what Borovic et al. Found, you can show that the measure converges to the long forward measure, which is the infinite maturity bond based measure. So this is not the same as recovering P independently of both Q and L. Either you get Q or you get L, and that's not the same as getting P. So the whole idea that the Perron-Frobenius theorem gave you the P measure, it did not give you the P measure. It gave you basically assumptions under which P would converge to either Q or L. So this problem does not afflict some other models like Martin, Schneider, Trajani, and all of that, which we will talk about later. So the motivation, why do what Ross did? So one of the motivations is that the unconditional or conditional estimates using historical data, they will not give you physical probabilities. Maybe history does not repeat itself. So then what do? You use the current prices of financial derivatives to provide forward-looking physical probabilities using the Perron-Frobenius theorem like Ross does. Now the problems with historical data, yes, technology, industry, demographics, risk aversion, everything might be changing, so the history does not repeat itself. And this problem is much bigger for unconditional estimates than conditional estimates. So to solve this problem, maybe derivatives have some future-looking information, which is intuitive. But let's ask, what if Ross recovery had succeeded? Assume history did not repeat itself, at least unconditionally, and Ross recovery worked. Then what would we have found by now? We would have found that physical probabilities obtained using Ross recovery would be better than those obtained using unconditional estimation. We would be debating right now whether physical probabilities obtained using Ross recovery are better than those obtained using conditional estimation. But we're not even coming close to unconditional. And the whole motivation was that history may not repeat itself, so we're at least trying to beat unconditional estimation. But Ross does not even, the theorem does not even do as good as unconditional estimation. So here's the recovery paradox, which is the main part of my argument here. There's a fundamental theoretical inconsistency. The whole motivation of the theory is that history does not repeat itself. So you come from the past time to present time, and then you use the forward-looking option prices in this future repeats itself period by period by period. But the time zero is just a, time zero is time zero. Yesterday was time zero yesterday, and after a month, after 1 month again, we'll have time zero. So are we saying that history does not repeat itself here, but then future starts repeating itself at some time zero, which is today? So this is inconsistent. Either you would say history repeats itself and will keep repeating itself in the future, or if future repeats itself, then history also must have repeated itself. So there's a fundamental inconsistency, which contradicts the two assumptions which are in the Ross theory, which these assumptions basically make future repeat itself. And the motivation is the history does not repeat itself. So there's this fundamental inconsistency. The two assumptions are, as Jens has laid out, transition independent stochastic discount factor. This itself assumes a constant time preference parameter and transition independent marginal utilities. And then you got time homogeneous state prices, which is the more problematic assumption. You need this because to avoid parallel universes. So you use options of increasing maturities to figure out those transition state prices that you don't observe. Now, if you look at this, I got from Jensen's paper, and I think you already explained this very well, Jens, so I don't have to repeat this, but I just want to make a few points. That let's say you're in this current state where, let's say the index is at 1,000, and let's say the other state, the index is at 1,500. Let's say, just make up some numbers. Then what Ross's theory implies that not only future repeats itself, but it repeats itself in ways we know it should not. For example, consider volatility is, implied volatility is, let's say, 80% in the current state, and this is January. And let's say you come over here, you keep going, and you come to November. Now, we already know that volatility is highly mean reverting. So there's very little chance that at this 1,000 price, when you reach over here at this 1,000 price, you're in the same state, that volatility would be still 80% because it's highly mean reverting. But the tail probabilities over here, this tail, or tail state prices rather, this tail state price would be high because volatility is 80%. Due to time homogeneity, this will continue, and even in November, you'll be using a tail probability consistent with 80% implied volatility. So you're just stuck in that state of high implied volatility forever. So futures repeating itself in ways we don't even think history repeats itself. So this is like a major problem. And then another problem is because it tries to do that, this time homogeneity is such a problem, it leads to what Jens found, these crazy transition densities, with huge state prices around here, which should be close to zero. And because of that, you have to create, some economic restrictions, and those restrictions then lead to option pricing errors in parallel universes. So there's really no way out of this. There's no way out of this because of this structure. The structure is so restrictive that it will not give you much flexibility. It does not even give you, it cannot even be consistent with the stochastic volatility model. Forget parametric models, but you can't even allow stochastic volatility because there's only one factor here. The only thing that you can allow in terms of the volatility would be dependence on the stock price itself. So you probably could have something like a constant elasticity of variance model, but not in the parametric form that Cox and Ross found. It would have to be some model that is time stationary, and we know none of those models are time stationary. But even if you could find a time stationary model, it would have to be something where even if it's time stationary, it would have to be something that does not allow stochastic volatility. It can only allow one factor, and that is not realistic. Now, the assumption of time homogeneous state prices is very problematic. So there's an extension by Jensen, which is also independently derived by Jackwerth and Menner. And by this extension, you do not really need parallel universes. You can use increasing maturity option prices, and from that you can get all of the physical properties you need. So let's look at this assumption, the assumption that is needed, the first assumption. And the first assumption is transition independence of the stochastic discount factor. That requires a constant time preference parameter. If you go on Google and you search for, the area of research that deals with constant time preference parameter, you'll find a paper by Frederick et al. In Journal of Economic Literature, 6,700 citations, and that paper cites Taylor. And what do they find? Investors are, when they do surveys, this constant discount factor just doesn't exist. You have something like hyperbolic discounting with 345% over 1 month horizon, 120% over 1 year horizon, 19% over 10-year horizon. So this delta remaining constant, which is needed in the Jensen model and even in independently derived Jackwerth Menner, where you don't need the second assumption, you only need the first assumption. Even in that model, that is very inconsistent with economic data. Second, the transition independent marginal utilities ratio, which would be needed, that's inconsistent with every path dependent utility model, like the habit formation models, prospect theory models. There's a model by Bailey et al. In 2019 that applied prospect theory, cumulative prospect theory to option prices, and that model fits wonderfully, but that is also path dependent, not path independent. So this is what we get. Ross's theory basically gave two results. Under a flat term structure, P equals to Q. Under a non-flat term structure, P equals to the long forward measure. it never gave you a physical measure. It basically gave you assumptions under which the physical process will either resemble the risk neutral measure or the long forward measure. And Kin and Linetsky really, they analyzed this with empirical data, and they actually proved that P is not equal to L. And if P were to be equal to L, then there's a very nice paper by Hussein in 1992 where the long bond is the optimal portfolio and the Sharpe ratio would increase with maturity for treasury bonds. But Kin, Linetsky, and Ni, they show that the Sharpe ratio decreases with maturity for treasury bonds. And no one believes that the excess returns on the optimal portfolio are only 2-3%. We know the market portfolio, the whole equity premium puzzle is based upon 6-7% excess returns. So we know that this is not true. The long forward measure is not the physical measure. So now my final slide here is that the context of Jackwerth and Menner is only with the pure recovery models. These are models like Ross, Carsten, Yu, Kin and Linetsky, Walden, Martin, and Ross in the fixed income area, and also Jensen, which relaxed the second assumption. All of these models suffer from the recovery paradox. The motivation that history repeats itself does not carry on with the assumptions, which makes future repeats itself. So that obviously cannot be true. But this critique does not apply to the STF restrictions-based recovery models, which are Martin, Kremens and Martin, Martin and Wagner, Schneider and Trajani, Chabio and Ludis. So the recovery paradox does not apply to these models because these models assume very mild historical information. Like they'll assume there's a volatility risk premium. Now we know there is always a volatility risk premium, but the sign of the volatility risk premium will continue in the future. That's a very mild restriction. You know, it's not a very strong history repeats itself argument. So the context is basically pure recovery models. And in conclusion, I would just say this is a wonderful empirical paper, clear, concise, rigorous, meaningful. It, you know, just makes the case for what it sets out to do. And my main critique here is more about Ross theory, that the motivation of this theory just contradicts its assumptions due to the recovery paradox. And it does not recover the P measure. Instead, it gives very, very strong assumptions under which the P converges either to Q or to L. That was the main finding in Ross. These theoretical limitations don't apply to the STF restrictions-based recovery models, which I've already talked about. So that is my discussion. And thank you for the opportunity to discuss this paper.
All right. Well, thank you, Sanjay, for both providing a good summary of sort of the area and also some useful comments about other alternatives to pure Ross's recovery theorem. So the panelists can speak if they have a question, and if someone from the attendees want to ask a question, I can unmute you, or you can put it into the Q&A box. All right. So anything from the panelists want to bring up, or maybe something from Jens himself? Do you have some reaction to Sanjay's comments?
I'm very happy with the first line of the conclusion. So let's just leave it at that. It's a fantastic paper, and I fully agree.
All right. Well, that's very good. So I start the question. Peter, you have a question? No?
Yes, I do. Okay, yeah. Yeah, so I thought Jen's paper was excellent. I have nothing to say about that. I agree with everything said. I want to actually address Sanjay's recovery paradox. So just to define it as I understood it, it's that the motivation for Ross's approach is that history does not repeat itself, and yet Ross and his followers assume the future repeats itself. Okay, so my observation is that there's multiple motivations for looking at option prices to try to get P distributions. It may be that history does not repeat itself, and then there's the contradiction you point out, but it may be that history does repeat itself, and that the motivation for looking at option prices is that it's a rich data set. There's at any, at any one calendar point in time, there's multiple strike prices and multiple maturities available. Whereas if I look back, let's say 1 month to predict next month, I have one observation. So, so if we go with the motivation is to mine the rich structure of option prices, then I think the recovery paradox goes away. What do you think?
That's a good point you make, but to really go deeper into your point, then we should be looking at the time series of the cross-section of option prices over time. This is when you really will be getting that benefit of the rich option data set. Like, how does a very deep out of the money option of a very different strike over time, how does it behave, and how does it deepen, so if you can get a time series of the cross-section of option prices, yes, you're adding to the data set, but you're ignoring all that history. Only you're looking at is current 1 day of, you're just using 1 day of current option prices. That's all you're using. So you're ignoring most of the richness that would be afforded by a time series, a moving time series of cross-section of option prices. That's where
I think you want to compare one snapshot of option prices with a long historical time series. But let's say that feels like an unfair comparison to me. Let's say at any one point in time, I have kind of a history of the term and strike structure of option prices, as well as a time series of just the underlying asset. And let's say I feel that let's say I grant that, let's say probably the history has relevance, in fact, because of time inhomogeneity, okay? A shortcoming of Ross's approach, in my opinion, is that he assumes time homogeneity, which sort of makes history irrelevant, like it's enough to have, under his assumptions, the term and strike structure of option prices.
So I could, I could put it this way, that there are these series of models, the STF restrictions-based models, began with Martin, Schneider, Trajani, all of these papers, right? And these are great papers because in those papers, you can have the information, the rich information coming from option prices, as you're indicating. They also use only 1 day of data, current data, and they're able to get, a good prediction for the market return. But what they are doing is they are not making this very strong assumption of time homogeneity or transition independence of state prices. Those two assumptions, they're making neither assumption. All they're assuming is that if the sign of the volatility risk premium is a certain sign, that sign will continue. A very, very mild restriction, and they're finding good results. So yes, there is rich information in option prices, but Ross's assumptions make it so skewed in terms of time homogeneity that the pictures that you saw with Jen's paper, those transition prices are all over the place, and you're getting interest rates, monthly interest rates, 600% over 1 month to negative 100%, because somehow that's trying to fit the actual physical measure to the long forward measure. Because of the assumption implies that. So it does crazy things to try to fit.
It clearly does crazy things.
Yeah.
I just, it's clear for those of us who studied it closely that sort of what drives his prediction is the covariation of the short interest rate with the state variable. Okay, and let's say, I always thought that that's not going to be an important aspect in pricing of S&P 500 options. And sure enough, empirically, looking at S&P 500 options, there's just, no evidence to support the, that this covariation with, in other words, there's sort of a joint assumption that the state variable is the S&P 500, and that somehow, if you like, and that this covariation is important. So that's rejected. I always thought if it was ever going to succeed, one needs to use swaptions. Okay, so something where, so think of the state variable as say a 30-year bond yield or something like that. And then, using swaptions data, maybe there's hope for it. I guess we still need to assume time homogeneity, which I don't personally believe in, but at least, there's a fighting chance. I feel there's no chance at all looking from S&P 500 equity options, and Jen's paper definitely confirms that. So
I had one question for Jens. The question was, you find that interest rates are doing some very crazy things under your Ross basic. And then you start putting economic restrictions because you want interest rates to be a little more normal. So you go to Ross bounded and also on. But given the fact that Lars has shown, Lars' paper and Kin and Lenetsky, they've shown that the measure we're using is really the forward measure. It's not a physical measure, but forward measure becomes physical measure. So it's very connected to either Q or L. So it's very connected to fixed income. But the result you're getting when you fit the time homogeneity condition is that interest rates are going wild. Monthly 600% interest rate or minus 100% in different states. Isn't that itself a rejection? Like how about we present a theory like this? That the assumption, time homogeneity, conclusion, you should have at least some reasonable bond pricing, kernel or whatever, and look at the interest rates, they're wild, and then so it's rejected. You don't have to go any further.
No.
Because that's why
I think the problem actually creeps in from using these rather short-dated options. So a lot of the action is at the 1 month horizon. So any small pricing deviation that you're getting in terms of implied volatilities, and the options data is really, really noisy, translates in terms of these transition prices or transition state prices, translates to minute variations in those. And if you sum them up across one particular state, they can move away from one rather easily. They don't affect the prices that incredibly much, even though they're moving a little bit away from unity. But once you take that to the 12th power to get an annualized interest rate out of it, the error is really magnified. So it's garbage in, garbage out. You're having the noisy option prices. You're having a not very well identified system with all these moving variables you're trying to estimate, and they can move quite a bit without affecting the option price by very much. And if you then check for a criterion like the sum of those state prices, transition state prices, they can move away from one quite easily. Okay? I'm not sure if one should overinterpret noisy input data in a way to make now fundamental statements about, is this moving towards a forward measure or is this moving towards the P measure?
But
I think that's asking too much of the data.
But isn't this just, and I'll just say this and shut up, isn't that not decided yet? I mean, are really option prices that noisy, or is it that the time homogeneity is such a serious violation? We're saying that if implied was 80%, after 11 months it'll be 80%. We know that's
we're working with fitted midpoint bid-ask spreads and they're wide. You can drive a truck through there. So no, it's option pricing. Okay, and this is what I've been doing for 20, 30 years by now. Option prices are bad news. Okay? They're really, really noisy, and you got to calm them down. And there are a few people who can wrangle them. Peter is one of them, and we make a cottage industry out of being the ones being able to do that. Huh? So this is our competitive advantage. So I really think this is about as good as it gets in terms of what you can do with the input data. There are, however, two improvements one could think about. I'm not keen on doing them because they involve a lot of work. One is rather silly. That is cut off at the 3-month horizon. Liquidity is in the near month anyway, and we're doing this joint fit all the way out to 12 months where there is very little liquidity. and that the dynamics of pricing at the 12-month horizon are different from the 12 times convolution of 1-month pricing should be fairly obvious. So I think one can deflect a lot of that criticism by simply going for the near fit, concentrate on the first 3 months, do moving windows over there, say with daily shifts, and you're getting 3 months, 90, you're getting some 30 observations, and that might be good enough, 60 observations. That's one idea. The other idea I had, but this would actually be quite some work, that goes back to your critique of we're using this restrictive state space of S&P 500 returns. Now, nothing in Ross Recovery precludes you from using a state space, which is, say, some outer product of S&P 500 states and volatility readings. Okay? So if one were to cobble together a joint state space of S&P 500 is at 1,000 jointly with volatility is, and let's make it simple, volatility is low and volatility is high. Okay, so that you don't get it in zillion dimensions, but you're having a rather parsimonious setting of kind of like a regime switching model. A model like that, one might be able to estimate if there is enough time variation in both the S&P 500 movements and also in volatility movements, so that you get the separate states across a couple of days, and you're willing to aggregate the implied volatility surfaces over, say, a month or so, you might be able to get somewhere. I mean, that would be difficult, but
yeah, I mean,
it's a creative way to getting out of this hole.
I agree, first of all, that nothing in the Ross paper prevented that, but you'll need options that are written on, you know, both S&P 100 and implied vol in some way, right? Like, let's say on the product of the two or something like that. I mean,
well, ideally you have those joint options, but if you simply have the marginal options as a short time series, and there is movement in the 2 dimensions, and you only have the marginals, then you can still make statements about the joint distribution.
yeah, assume a copula is what you're saying. That's fine. I agree.
Yeah.
But Jen, I
All
think
right.
there's a problem here because the transition independence of SDF, that implies that the utility, marginal utility ratio, that ratio depends only on the underlying asset. It does not depend on volatility.
All right.
Because
Sanjay,